we have been discussing electric intensity due to various charged bodies, and now let us proceed to the some more charged bodies, and due to them let us find electric field intensity. So let me give a quick recap of the previous class. In the previous class, what we did is we found E due to a point charge, E due to a point charge. That means whenever some charge is here at a given point, a distance r, the E value is k q by r square. This is what we did previously. Okay. Now next one, I went on explaining you E due to a uniformly charged rod, and the two cases we have taken there. This is one charged rod of length L and of charge Q. Then on the axial line at a given point, the value of E comes out to be kq by L into 1 by R. This is let us suppose the distance is R here from one of the ends, minus 1 by R plus L. So I think this is the formula we derived. Just verify it again if you have any doubt. And one more concept we undertook here, that is the point is on the bisecting line, the equatorial line, exactly at the middle, and some distance R. The length is usually L and the charge is Q. And in this case, we got an equatorial line. Let me write here on the equatorial line. This is on the axial line. Okay, on the axial line. What formula we got is 2kq by R under root of L square plus, we might have got like this, R square plus 4L square. You just verify it again. Okay, this is the formula we derived in the previous case. And not only this, then we next step what we did is E due to infinite uniformly charged. Let me write here, due to uniformly charged infinite rod, or we say sometimes thread. So pictorially let me show you here. This is what we have taken here. This is the length goes on extending to the infinity in either direction, and at a perpendicular point here at a distance r, we got some formula like this. I think this is what we did. This is what r, the distance is, this is r, where lambda was linear charge density. Lambda was linear charge density, that means charge per unit length. So these derivations we made, and these are the synapses of those derivations. Now from this, let us proceed further. Let me proceed to the next topic. See, after every class, after writing the old derivations, you made the concepts like this at the end of the chapter. Because for the entrance examination, you need to remember the formulas. Anyway, you must understand the derivation and you must remember the final equations. And don't do that mistake. Without understanding the derivation, don't go for remembering only the final formulas. It will be very difficult to remember them without knowing the process of derivation. Okay. Now, let us get into the next one, that is E due to a finite uniformly charged rod. And let us come to the infinitely charged rod from that condition again. Now, so let us say, let us take like this. This is a rod, uniformly charged rod of finite length. It's not infinite length. And at an arbitrary point, it's not perpendicular at arbitrary point. Already we have seen exactly at the middle here, equatorial line. So the same rod we are undertaking again, but here the only difference is the point is somewhere, it's not along the equatorial line. So it will be like this, and this is some distance here, you can take R. As usual, the dimensions is L is the length of the rod, and Q is the total charge on it, and lambda you can say linear charge density. The meaning of that is charge per unit length. So lambda equal to what? Q by L. Now let us take this one. This is some angle theta 2 and this is some angle theta 1. So this point is making an angle theta 1 with this end of the rod and theta 2 with the other end of the rod. This line is making those angles. And to find the intensity, the usual procedure is same. The procedure we adopt is same. We have to differentiate this into elements. So this is what P is, and this distance what I said R. The usual procedure is you take one element here, this is one charge element where the charge on this is dq, and the distance is, this distance is something x, and here this is making an angle theta with this. Naturally, once you find the intensity because of this element, then you integrate from theta 1 to theta 2, the total rod will be covered. So the intensity because of this element is dE, and this angle will be also theta. See here, this angle will be also theta. Resolve this into two components. This is, see, adjacent to is, this will be dE cos theta, adjacent is dE cos theta, and this will be what? dE sin theta. And see, they will not be cancelled as we did here. In this case, for every element here you will find other element, for other element you will get, so therefore horizontal components cancel. But here you don't find an exactly pair element here, therefore this will not be cancelled. Therefore we will be getting the two intensity values here along the x-axis, along the y-axis. Therefore along the x-axis, in order to find Ex, you have to integrate dE sin theta. In order to find Ey, you have to integrate what? dE cos theta. Then once you got Ex and Ey, E will be under root of what you say, Ex square plus Ey square. This is the general procedure. This overall map you must have in your mind before seeing the derivation. Now let us do one after the other. So first of all, what is dE? dE because of this element. What is the distance here? This distance is, this is R and this is x, and this will be under root of R square plus x square. And the dE formula is generally K into the charge on the element, by the square of the distance, When you square the distance, the root will be dropped. Therefore you will get R square plus x square. This is dE. But dq, what you can write? The length of this element. Always take the length of the element. When you assume length of the element is dx, then dq can be written as the charge in the 1 unit length into the length of the element. So dq equal to lambda dx. So therefore let us substitute the dq value here. What you will end up is k lambda dx by R square plus x square. So this is what dE is. Then how will you find Ex? dE sin theta and dE cos theta. Now let us write sin theta also here. You take this triangle, sin theta is opposite by hypotenuse, therefore x by under root of R square plus x square. Similarly cos theta is what? Adjacent side by hypotenuse. Adjacent side is what? R by under root of R square plus x square. So with these values, we know dE and we know sin theta and cos theta. These you have to evaluate now. Therefore let us find first of all Ex, that is nothing but dE sin theta. Let me write directly because you have seen here dE let me substitute the value of d there, k lambda dx by r square plus x square, and sin theta is x by under root of r square plus x square. And if you simplify this, k lambda, you can write x dx by r square plus x square to the power of 3 by 2. Lambda always you can substitute what? Q by L. You can substitute here Q by L. That is a constant one. Now, you have to evaluate the integral. From where to where you have to evaluate? Here on theta here. If you are integrating on theta, it should be theta 2 to theta 1. Therefore, minus theta 2 to plus theta 1, it will be covered. So, therefore, I will change x value here as we did yesterday. Very similar procedure. Anyway, let me explain you again so that you will be very perfect in the integration here. X equals to r tan theta. Let us put x equal to r tan theta. So, in this step, when you come across here, you have to evaluate the integral anyway. So, I am explaining you how to evaluate the integral here. X equal to r tan theta. Then dx equal to what? R sec square theta into d theta. With these substitutions, this integration makes, let me take you 1 points here. This is an equation, okay, this is 2, 3, this is better always, right, better practice, this is 5. So, Ex equal to, you got this one. With this substitution, what it makes is, Ex will be, so k lambda, let me take k lambda outside of the integration, that's better always, right, because that is anyway constant. X is r tan theta, and dx is, what you will get is r sec square theta d theta by, what is here is, if you substitute here r tan theta, this will be r square tan square theta, then r square can be taken common, r square into 1 plus tan square theta. 1 plus tan square theta is nothing but sec square theta. So, you will get r square sec square theta to the power of 3 by 2. You will get that. And naturally, these squares will cancel here, cube remains. So, you will end up with like this, r square, this r into r square tan theta sec square theta d theta by, this will be r cube sec cube theta. So, what remains is, see, r square, 2 r's will cancel, sec square, 2 sec will be cancelled. So, tan theta is nothing but sin theta by cos theta, sec theta is nothing but 1 by cos theta. So, cos thetas will also get cancelled out. Finally, what remains is, you will get sin theta d theta by 1 of the r you will get. And this r you can take out of the integration, k lambda by r, integration is done minus theta 2 to minus theta 2 to plus theta. You can either take minus theta 1 to plus theta 2, doesn't matter, it doesn't make any difference, right? Minus theta 2 to t1. So, sin theta d theta. The integration of sin theta is nothing but, you will get minus cos theta, that is the integration of sin. So, this will be minus theta 2 plus theta 1. Let me write here, Ex then k lambda by r minus cos theta 1, minus cos theta 1, minus of minus plus cos of minus theta 2, that is nothing but cos theta 2 from the trigonometric results, right. Therefore, finally, you can write k lambda by r cos theta 2 minus cos theta 1. So, this is the important final result. Let me say this is equation number 6. And similarly, we have to evaluate what Ey. Let me write Ey here. Ey, how you can integrate is dE cos theta. dE is given, cos theta is given. Therefore, k lambda dx dE by r square plus x square into cos theta is r by under root of r square plus x square. So, k lambda is taken out of the integration. Then what you will get is r dx by x square plus r square to the power of 3 by 2. Again the same substitution here, x is r tan theta, dx is r sec square theta. I am writing directly there, k lambda, right, r, dx is very similar, r sec square theta d theta, by this will be very similarly what you will get, r cube sec cube theta. So r square, this r cancel, right, sec square, this sec cancel, and what you will get is 1 by sec theta is nothing but cos theta you will get. Therefore k lambda by 1 r already remained here, r integration of cos theta d theta. See here, if you compare, the only difference is here we got earlier sine, now we got cos, and the integration should be done from minus theta to plus theta 1. What is the integration of cos? The integration of cos is sin theta, and the limits are minus theta 2 to plus theta 1. Then substituting the limits, what you will get is k lambda by r sin theta 1 minus sine of minus theta 2. Sine of minus theta is minus sine theta. Therefore, you will end up with plus sine theta 2. So, finally, we got the formula for Ey, k lambda by r is equal, into sine theta 1 plus. So, this is the Ey component, the vertical component of the electric intensity. And once you know Ex and Ey, you can find what E is under root of Ex square plus Ey square. If you have any doubt anywhere, rewind the video and then look again. That's always better, right? So this is what we found, the value for E due to uniformly charged rod at arbitrary point, and very small, it is not infinite one. Now, if you remember these two formulas, immediately you can get back to all these relations. I will show you from those equations how we will come across again these relations. Okay. Now, so students, it is very important. Now, I will correlate these derivations with our previously derived facts. Now, in the case of the uniformly charged rod, this one at exactly the bisecting point, right, at exactly bisecting point, then naturally what you will get is theta 1 is equal to theta 2 here, theta 1 is equal to theta 2. So, what you will get is, definitely in the previous case there was no Ex component, therefore Ex should be 0, Ex is 0, and from that k lambda by r cos theta minus cos theta, you will end up with 0. That was this case, right? And you will also get Ey. What was Ey? K lambda by r, you will get sin theta plus sin theta, that is nothing but 2 sin theta, 2 k lambda by r into sin theta. And lambda is sin theta, what you can write here, this is in this case the total length was L and this is L by 2. So, sin theta can be written as L by 2 opposite by L by 2 by under root of what you can say hypotenuse, that is r square plus, what is the hypotenuse here, under root of L square by 4 plus L square plus L square by 4 plus r square. So, what you will get is, you will get L square plus 4 r square by 4, right. So, that means you will get L square plus 4 r square by 2 you will get. This 2 cancel out here. Then what you will get is 2 k lambda by r into L by under root of L square plus 4 r square. So, just a small correction here, you get into the L square plus 4 r square. See, we got the same answer here, and one important thing is lambda equal to what you will get. Just now I mentioned lambda equal to Q by L. See how you got the previous result exactly from this one. LL cancel. LL cancel. See, you got this equation 2kq by r into under root of L square plus 4r square. So this is how this derivation is related to our the past derivation. This is one thing I would like to explain. And the next one, the more important one is due to the what you can say is infinitely. What is the other one we derived? E due to uniformly charged infinite rod. In the case of the infinite rod, here, this is one case we went back. The other case is this is infinite thread. What will be the angles then? The angles will be, this will be like this and this will be like this. This will be 90 and this will be also 90. That means theta 1 and theta 2 almost infinity. It is matching somewhere there. With this line it is making 90, this is matching somewhere there, this is also 90. So therefore, Ex will be equal to, what you will get here is k lambda by r is the distance anyway we have taken previously also, cos 90 minus cos 90, cos 90 is anyway 0, therefore you will get 0 there. So previously also there was no x value here, only we said E, that means only y component here. And what is the y component? The y component was k lambda by r sin theta 1, that is 90, plus other one is also 90, 1 plus 1 is 2, therefore you will get Ey is nothing but Ey is 2k lambda by r, there is no Ex, therefore you can say E is, you can say 2k lambda by r. So this is what the previous result we got in the case of infinitely charged rod. And one more important point I would like to mention here is this, without derivation I am giving the next answer, without the derivation I am going to give the next answer, that is E due to semi-infinite charged rod or thread. So this is without derivation we can make out of the previous derivation. That means the rod is like this, it is semi-infinite, means the rod extends up to infinity and the point where we want to find out the intensity is at one of the ends. Therefore this is called semi-infinite. While deriving this equation, try to remind yourself we integrated from minus infinity to plus infinity, because this is infinity in this direction and infinity also in this direction, but here it is extending only in one direction to the infinity, and this, the result for this is without derivation we can obtain from our previous formulas. See here, if you take any element here at this point, this is dE and this can be resolved into, this is theta, this is dE cos theta and this will be what? dE sin theta. That means Ex and Ey. And one important thing is, for the other end, if you want to join the other end, somewhere in infinity, the initial angle was what here? 90. The theta 1 is 90. The theta 2 will be what? One of the angles will be 90. You can call it as theta 1 or theta 2, doesn't make any difference. The other angle will be, initially it is 90 with this edge. What is the 90? The point making with one of the ends of the rod, that is 90, straight, perpendicular. With the other end, what it makes? The other end it makes 0 degrees because that is infinite located, right? Infinite located. So therefore, instead of finding Ex is what actually you have to find dE cos theta. Ey is what? You have to find integrate dE sin theta. So instead of doing all this, instead of doing again the laborious derivation, we can simply find the answer by the previous equations. What are the previous equations we derived for that rod? K lambda by r cos theta 1 minus cos theta 2. So what is theta 1 here? What is theta 2 here? You can take one of them is 90, cos 90 is 0, cos 0 is 1. So minus depending on the direction here, don't bother about that. This is, you can take theta 290 or theta 10. That is convenient. There is no problem with that. So theta 2 is 90, cos 90 is 0, cos 0 1. What you will get? Ex is what? K lambda by r. This is the first equation. And Ey, what you can find is, Ey, what's the formula we derived? K lambda by r sin theta 1 plus sin theta 2. Theta 1 is what here? 0. Theta 2 is what? 90. Sin 0 is 0. Sin 90 is 1. Therefore, K lambda by r. So, Ey also K lambda by r. Then, what is the net intensity because of this? Intensity is under root of Ex square plus Ey square. What you will get is root 2 K lambda by r. So, this is the final answer I would like to give you is. So, this is due to semi-infinite charge rod. So, this is one more derivation, one more formula you can write under the synapses. Okay. So, these are the only verifications. So, this is a verification already we derived. This is also verification already derived. But this is another new derivation. With the help of the previous result, we got the answer. Therefore, you need to write under the synapses here. Now, let us move into the other one. To the next concept, that is E due to one more important derivation, E due to uniformly charged ring. Uniformly charged ring. Now, so we are discussing another charged body which is in the shape of a ring. So, this is a ring where the charge is distributed like this. Let us suppose the radius, you can define the physicalities here. The physicalities is the radius is something r, the total charge is something q, and here also we can define the charge density. The charge density is again, let us suppose lambda, linear charge density, because this is on the circumference, you can say, that is nothing but q by circumference is what? 2 pi r. So, this is what the physicality of the charged ring. Now, the question is, at the center, let us take up this case, what is the electric intensity at the center? That is very simple to answer. So, now, again if you think in this manner, if you take up one charge element here, the intensity, very small finite element you can imagine where the charge is dq, and at the center this will be anyway r, the intensity will be in this direction, and immediately you can imagine a counter element exactly diametrically opposite to that. Then because of this element, the intensity will be in this direction. The charge is same, the distance is same, therefore, the net intensity is 0 here. You take any element anywhere, you will be finding a counter element on the other direction, therefore, they will be also cancelled. So, because of the mutual cancellation of all the intensities, E at the center is 0. E at the center is 0. Because the one point here is, you have to understand the charge is symmetrically distributed. You try to make this a note. Take a note of this. Charge is symmetrically distributed. In such cases, not only this, I will give you some more examples. So, whenever the charge is symmetrically distributed, at the center of the symmetry, the intensity will be 0. So, whenever the charge is symmetrically distributed, at the center of the symmetry, at the center, E will be generally 0. For example, this is an equilateral triangle. Equal charges are, that is also important. Equal charges are placed like this at the corners of equilateral triangle. Then what will happen is, exactly at the center, that means here centroid we call centroid, or you can imagine a circle around these charges here. This is the center of the circle and centroid of the equilateral triangle, symmetrically distributed. Therefore, you can say at the center, this is center C, let us denote at the center it is 0. Not only this, for example, you can also take a square here, you can take a square. This is some plus q and equal charges are taken in a plane, and exactly at the center you can say, again without any further derivation, you can immediately say, because the charges are symmetrically distributed, you can construct even a circle around this. The center of the circle is exactly the wherever the diagonals intersect. Therefore, E at the C is again 0. And not only this, any regular polygon if you take, suppose if you take a pentagon here, you take a regular pentagon here, at the center here, wherever all of them meet, right? Okay, you can just take some center here that is equidistant from all of them. So that is equidistant from all of them. A, let us suppose this is center. Again you can say at the center, that means you have taken charges at the corners of the vertices of this regular pentagon. E at C is again 0. E at C is again 0. So one important thing is, in the entrance examination, if this is given like this, suppose the uniformly charged ring, the same charged ring if you take, it will not be asked in the examination straight away, but there will be some modifications will be made, and the question is constructed. Suppose a small cut is made, of thickness T. Small cut is made by the thickness T. Then the charge is everywhere there, but except in the small cut there is no charge in the cut, isn't it? That is a vacant site. Now what is the intensity at the center? That will be the general question. It is no more 0 now, because this vacant site is having one counter charge here. This charge element do not find any counter charged element here, therefore this will not be cancelled out. All the other occurs in pairs. For example, if you take this element, you will get another pair here. If you take this element, you will get another pair here. The effects of them will be mutually cancels out, but effect of this will not be cancelled out, because there is no charge element or the pair of the element on the other side is present. So therefore, because of that, you will be having some electric intensity there, and that intensity, what you can say is, K dq. Let us suppose here, what is the charge there? dq. By what is the distance here between the point here? The distance is r. So therefore, K dq by r square. What is the direction of that? The direction of this is, the direction of A is towards the cut. Direction is towards the cut. Wherever we cut the ring, the direction will be in that direction, right? And what is the dq here? dq is nothing but lambda into t. R you can take dt, whatever it is, r, w you can take, dx you can, it's your wish, but t indicates not the time here, thickness that is cut there. So lambda is nothing but charge per unit length into length of this cut. What is the charge per unit length? I said lambda is somewhere I wrote here, q by 2 pi r into t. With this substitution, therefore, what you can say is, at this center is qt by, already r square is here, this is r, this is 2 pi r cube. So this will be the answer. Don't try to remember this equation, because this is very simple to derive then and there. So don't try to remember this, okay? And next one, one more simple application I will give you here of this concept of the symmetry. Suppose there is a regular pentagon is there, very similar to this, okay? Okay, regular pentagon is there, and what is given is, the charges are only given 4 in number. 4 charges are given, and this charge is absent there. This is removed, and this is removed here. Previously, just now I told you the electric intensity at the center is 0 because of all the charges are at the vertices. One charge is missing out here. What is the electric intensity because of the remaining 4 charges? How you can do in a very simple manner is, so I can write E due to 5 charges, E due to 5 charges is 0. I am writing again, right? So this E due to 5 charges can be written as E due to 4 charges, E due to 4 charges plus E due to 1 charge. Can you write like this? Yes, we can write, because I have taken 4 and 1, right, equal to 0. Therefore, E due to 4 charges in magnitude is nothing but, in magnitude, forget about the direction, in magnitude it is nothing but E due to 1 charge. E due to 1 charge. And what is the distance here? It is A. So therefore the question is what? E due to the 4 charges, not about the 5 charges. So if you find E due to 1 charge, that is exactly same as E due to finding 4 charges. So it's very simple now. E due to 1 charge is simple. Forget about the all remaining charges. That is nothing but KQ by A square, because the distance is A. This will be the answer. And what is the direction? Remember always direction towards the vacant sum. Here I have given only the magnitude. Now I am telling the direction also. The direction is towards the cut here. Direction is towards the cut or the vacant side here. In this direction, the final E will be lying. So here we simplified the problem of finding intensity due to 4 charges into the problem of finding E due to 1 charge by simple understanding of the symmetry charge distributions, where we started from a charged, uniformly charged ring. So this concept keep in your mind always, useful for the many numerical solving many numerical problems, right? I will quickly move to the next one, uniformly charged ring on a different point. Okay. Now let us take one more derivation, one more important formula for the charged ring, but the point is on its axial point. So imagine this is a charged ring. Actually, you imagine the ring out of the board like this, out of the board. It's not on the plane, it is out of the board, and this is the radius is something capital R, and this is something let us take small r here, that's a variable. So this is the center of the ring. Let us denote by O or C. This is a point where you need to find the intensity because of the whole charged ring. So here the charge is distributed on the ring like this. Okay. So what is the radius of the ring? I said R. What is the circumference of the ring? 2 pi r. Therefore lambda you can define. Lambda is nothing but, I said, linear charge density. So linear charge density is nothing but lambda is q by 2 pi r. Now in order to find the intensity at the point P, what we do is we divide this into small elements. One such element, let us take here, of the length dl, and immediately you will get one more pair of element here, dl. See, actually this is out of the board like this. You are taking one element here, and at the point P you are considering, and here also at the point P you are considering. This is the way to imagine. This is not on the board, but out of the board like this. Q is the element I have taken on the top of the ring, and other element at the bottom of the ring. Now if you join this one, this point, the intensity because of this particular charge element, where the charge can be taken dq, small charge is there, and this will be, the distance will be naturally under root of r square plus r square, and this is, let us suppose, something theta, and if you extend this axis, this is also theta. You can resolve this into two components. This is dE cos theta, and this will be dE sin theta, and you can again have the one more, the counter element. This is also dE, this is also theta. By symmetry, this is also theta. You will be getting another dE cos theta and dE sin theta here. So dE sin thetas, because of not only the two elements, for all the elements they are mutually opposite. For all the elements, dE cos theta will be added. So dE sin theta will be cancelled out. Therefore E is nothing but integration of dE cos theta. Now the simple point is, if you find dE and if you find cos theta and integrate, you will get the answer. What is the dE now? dE, the previous expression, equation, k into dq by square of the distance between the point and this point. What is the element here, and the distance is what? Under root of r square plus r square. Square you take, what you will get is r square plus r square. So this is dE. What is cos theta there? Cos theta is nothing but, cos theta is adjacent side by hypotenuse, that is r by under root of what you can say is r square plus r square. These two values substitute here, then what you will get is E equals to integration of dE, that is k dq, r is there by what you can say is r square plus r square to the power of 3 by 2, r square plus r square to the power of 3 by 2. But what is dq here? dq is nothing but lambda, that is charge per unit length into the length of the element, the charge per unit length into length of the element. So what you will get is lambda is what? Q by 2 pi r into dl. Let us substitute this one here. Then what you will get is k r dq is nothing but q by 2 pi r dl comes here, and what is here? R square plus r square to the power of 3 by 2. What are the constants here? See, r is constant, that means you have taken a point at a distance r from the center, that is constant, and the radius is constant, and this is also constant, and the total charge is also constant. So take away those constants out of the integration, what you will end up with is k I am taking out, r I am taking out, q I am taking out, 2 pi r is a constant, r square plus r square to the power of 3 by 2 is also a constant. I have to integrate dl. So when you integrate dl, what is the integration of dl? You have to add all the elements here. You have to add all the elements. Integration of dl means circumference. You will end up with like this, k q r into 2 pi r by 2 pi r into r square plus r square to the power of 3 by 2. This you can cancel straight away. So therefore E will be k q r by r square plus r square to the power of 3 by 2. This way you can remember. If you want, you can substitute 4 pi epsilon, 1 by 4 pi epsilon naught there. So E value is 1 by 4 pi epsilon naught q r by r square plus x square to the power of, sorry, r square plus r square to the power of 3 by 2. What is small r here? Always remember, from the figure, small r is the distance from the center of the point. Immediately you have to understand one thing here. At the center, what is the value of, previously we got this result actually. Before this derivation, what I was telling you is electric intensity at the center of the ring. From this equation, you must get back to the old result. Always verify like that. At the center, r equal to what? 0. That means the point comes to center, r becomes 0, then E value becomes 0. This result already we got. And not only this, another point you can make is when r is much greater than r. That means, what is the meaning of that? The point is at very long distance from the center. In that case, you can neglect this r square compared to the r square. Then what you will end up with is 1 by 4 pi epsilon naught q r by, what is, I said r is much greater than, this is negligible, therefore you will get r cube, you will get r square. So this is also the very result you must expect. So why you must expect is, when the distance is more, this whole charge ring, if you are looking from a long distance, this charge ring should look like a what? A point charge. For a point charge, what already we know is, this is k cube by r square. The old result you must get back from this equation. I will explain more about this. This is a very important one in the next class. So just go through it, the whole class, and make your own notes, make your own synapses. That will help you a lot. If you ignore or if you neglect, you will be landing in very difficult situation later on in the due course, right? Thank you. See you again.